Hi, this is chapter 8.4, length contraction. We've seen at the beginning of special relativity that two observers moving relative to each other will measure the same exact relative velocity. Well, this has an interesting implication. So first, let's go back to the formula we've seen in chapter 8.3, time dilation. So we've seen that delta T2, or the time for the person at rest, is equal to the relativistic factor, or gamma, multiplied by the time elapsed in the moving frame. All right. Now in chapter 8.4, to do the derivation, they do a slight change in notation. Instead of using delta T2, they use delta T0, and they call this the proper time, or the time elapsed in the frame at rest. Now the remaining of the formula is identical. All right. So let's have a look at what happens if the velocity measured in both frames is the same and stay constant. Basically, we have here L0, which represents the proper length. This is the length measured in the frame at rest, divided by delta T0, the proper time. So this distance divided by time is obviously the velocity. Now, from the point of view of the moving frame, we have L1, and in our note they use simply the L. So I wrote it like this, but L1 or L for me mean the same thing, divided by delta T1. Now these two have to be equal, and if we look at the previous formula, there's this relationship between delta T1 and delta T0. So we can use this relationship to replace delta T1. And once we replace delta T1, we see that the both time cancel out. We can cancel out delta T0 on both sides, and we are left with the proper length equal to the length multiplied by the relativistic factor. And when we isolate, we get this formula. And this formula has an interesting consequence, is that if we measure the length of anything relative to our frame, we find its length to be smaller than the proper length. And that's a bit weird, because no matter in which frame you are, you always feel, unless you're accelerating, you always feel that you are at rest. So if you measure a frame moving with relative to you, you will always measure a shorter distance than from the point of view of the person that's inside that frame at rest. We will see many examples here because it's not easy to grasp at first. So let's go solve some example, and hopefully it will be more clear at the end.